Hello, everyone, and thank you for joining us on today's webinar. Good morning, good afternoon, or good evening, wherever you are in the world today. My name is Brenton Harris, and I am the Vice President of Sales and Marketing here at the ProtectWire Company. To those of you that have listened to any of our legacy webinars, welcome back. And for those of you that this is the first time joining us, please note that we have a variety of webinars available on our website. Unlike today's webinar, most of our legacy webinars have focused on our linear heat detectors and the applications where that technology can be applied. ProtectWire has been manufacturing linear heat detectors for over 85 years. However, recently, we've expanded our product portfolio to include several new complementary products, so please stay tuned for additional webinars as we'll be focusing a bunch of new products soon. As you know, today's webinar is focused on thermal imaging cameras and their use for pre-fire visual thermal detection monitoring. In the first half of the webinar, we'll introduce the technology and operation used within the thermal imaging cameras. This will be presented by Brian Harrington, our Vice President of Manufacturing. The second half of the webinar will focus on some common applications where this technology can be applied. Please note that while the presentations are happening, we will be enabling the live chat feature found on the right side of your screen. Please post your questions in the thread as they develop. Okay, let's get started. I'm now going to turn it over to Brian Harrington. Brian?
My name is Brian Harrington. I'm the Vice President of Manufacturing at the ProtectWire Company, and I will be your presenter. This presentation will introduce you to the Planck Vision Systems thermal imaging cameras offered by ProtectWire Fire Systems. These cameras are utilized in pre-fire detection applications, providing real-time thermal monitoring and early thermal event detection. These thermal cameras are provided by ProtectWire through our partnership with Planck Vision Systems. ProtectWire and Planck Vision Systems have partnered to combine our technology and industry expertise to improve fire prevention using the early detection capability of visual thermal monitoring. The ProtectWire Company, located in Pembroke, Massachusetts, was established in 1938 by Gerald and Sarah Holmes, who invented and patented ProtectWire digital linear heat detectors. Over the last 85 years, ProtectWire has established itself as an industry leader in linear heat detection and special hazard fire detection. ProtectWire continues to expand its product offerings to best serve its customers and meet their needs for process and facility protection from overheat and fire. Planck Vision Systems, a solutions-based manufacturer of dual vision network cameras, is headquartered in Santa Barbara, California, the capital of infrared sensing technologies in the USA. The Planck team has more than 20 years of experience providing thermal and visible camera solutions to their customers. Their diverse offering of dual vision network cameras with powerful on-edge analytics are distributed worldwide. Let's begin by discussing what is infrared radiation. Infrared radiation is a type of electromagnetic radiation that has longer wavelengths than those of visible light, but shorter wavelengths than those of radio waves. Infrared light is not visible to the human eye, but it can be detected by specialized sensors and cameras designed to work in the infrared spectrum. Here are some key characteristics of infrared light. Infrared radiation typically covers a wavelength range between approximately 700 nanometers to 1 millimeter. This range is subdivided into three main categories: near infrared, from about 700 nanometers to 1400 nanometers, mid-infrared, from about 1400 nanometers to 10,000 nanometers, and far infrared, from about 10,000 nanometers to 1 millimeter. Infrared light can be detected and used for various applications, including thermal imaging, night vision, remote sensing, and communication. Infrared radiation is associated with heat, and it's often used to measure temperature and thermal patterns. Warm or hot objects emit more infrared radiation than cooler ones. There are both natural and artificial sources of infrared radiation. The sun, a natural source, emits significant amounts of infrared radiation, which we can feel as heat. Other natural sources include warm objects like animals, the Earth's surface, and even the human body. Artificial sources of infrared radiation are things like heating elements, infrared lamps, specialized light bulbs, and electronic devices. In summary, infrared light is a form of electromagnetic radiation beyond the visible spectrum, primarily associated with heat and used in a wide range of applications for detecting, imaging, communication, and temperature measurement. The discovery of infrared light is attributed to Sir William Herschel, a British astronomer and musician in the early 19th century. Herschel conducted experiments in 1800 to study the distribution of heat in the spectrum of sunlight. During his experiments, he used a prism to disperse sunlight and measure the temperature of different colors. He observed the temperature increased as he moved from the violet end of the spectrum, composed of shorter wavelengths, to the red end, which was composed of longer wavelengths. Intrigued by this finding, Herschel went beyond the visible red light and found that there was an even higher temperature region beyond the red part of the spectrum. This part of the spectrum he termed calorific rays. The discovery of the invisible higher temperature radiation beyond the visible spectrum laid the foundation for understanding infrared radiation. Herschel's work opened up a new realm of study in the electromagnetic spectrum, and the term infrared was coined later to describe this region of the spectrum, where wavelengths are longer than those of visible light but shorter than those of radio waves. An electromagnetic wave is a fundamental form of energy that consists of oscillating electric and magnetic fields propagating through space. These waves are generated by the motion of electrically charged particles and do not require mediums such as air, water, or solids to travel through. Electromagnetic waves can propagate through a vacuum. Electromagnetic waves have a wide range of applications, including communications, such as radio, TV, and mobile phones, medical imaging, such as X-rays and MRIs, cooking, such as microwaves, remote sensing, such as radar, thermal imaging, and many more. The electromagnetic spectrum encompasses a vast range of wavelengths and frequencies, each with unique properties and uses, making electromagnetic waves essential in modern technology and our understanding of the physical world. The electromagnetic spectrum is a continuum of all electromagnetic waves, organized based on their wavelengths or frequencies. The spectrum includes from longest to shortest wavelengths radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. The infrared spectrum encompasses a range of electromagnetic waves with wavelengths longer than those of visible light, extending from the near infrared to the far infrared. All objects emit thermal radiation in the infrared spectrum. Long-wave infrared radiation, specifically in the 6 to 15 micron wavelength range, is commonly used in thermal imaging for a few reasons. One is thermal emission. Objects at normal room temperatures emit infrared radiation in the long-wave infrared range. The amount of radiation emitted is directly related to the object's temperature. This makes long-wave infrared ideal for capturing the thermal signatures of objects and scenes. Two is atmospheric transparency. Long-wave infrared radiation is less affected by atmospheric conditions such as fog, smoke, and haze, compared to shorter wavelengths. This is important for applications where visibility might be compromised. Three is detection of temperature differences. Long-wave infrared is sensitive to small temperature differences. This sensitivity enables the detection of variations in temperature that can be crucial in various applications, including medical imaging, surveillance, and industrial inspections. 4 is operating temperature. Long-wave infrared sensors can operate at room temperature or slightly higher, reducing the need for expensive cooling systems. This also contributes to lower background noise in the images and makes the systems more practical and cost-effective. In summary, long-wave infrared is well suited for thermal imaging due to its compatibility with thermal emission, atmospheric transparency, sensitivity to temperature differences, and practical considerations like low background noise and operational temperatures. Infrared radiation has some unique properties to consider. Some materials that are transparent in the visible spectrum of light are opaque or reflective to long-wave infrared. One example is common silica glass. As seen in the top image, the thermal camera does not see the view outside the window coming through in the visible spectrum. Instead, the camera sees a reflection of long-wave infrared coming from the interior of the room. The thermal camera is unable to see through the glass. Some materials that are opaque in the visible spectrum are transparent in the long-wave infrared range. One example is smoke. In the middle image, we show how a black plastic sheet is opaque to visible light, blocking the view of the subject's arm. When viewed in the long-wave infrared spectrum, the black plastic sheet is transparent, allowing us to see the subject's arm. One misconception is that thermal cameras can see through walls. This is not the case. As seen in the lower example image, thermal radiation from inside the structure affects the outer surfaces, making them visible, but what is behind the walls cannot be seen. Due to common silica glass being opaque to infrared radiation, special lenses and windows are needed to view in the infrared spectrum. Infrared lenses are made from various materials that possess the ability to transmit and focus infrared radiation. Infrared radiation has longer wavelengths than visible light, and these lenses are designed to be transparent in the infrared spectrum. The choice of materials for infrared lenses is influenced by their transparency to IR wavelengths and their optical properties. The choice of material depends on the specific application, the desired infrared wavelength range, and other factors such as cost, durability, and manufacturing considerations. Different materials have varying transmission characteristics and are suitable for different ranges within the infrared spectrum. An object's total infrared radiation output is a combination of reflected, emitted, and transmitted radiation. It's important to consider this when calculating an object's temperature based on its observed infrared radiation output. Reflected refers to infrared radiation that is reflected off a surface or object. When infrared radiation from a source, such as the sun or a heat-emitting object, strikes a surface, some radiation is absorbed and some is reflected. The reflected infrared radiation can carry information about the temperature and composition of the reflecting surface. For example, in thermal imaging, sensors detect and interpret the reflected infrared radiation to create thermal images that reveal variations in surface temperatures. Emitted is the infrared radiation that is naturally emitted by objects or substances due to their temperature. All objects emit infrared radiation as a function of their temperature according to Planck's law of blackbody radiation. The intensity and spectrum of the emitted infrared radiation depends on the object's temperature and emissivity, a measure of how efficiently an object emits infrared radiation. As an object's temperature increases, the amount of emitted infrared radiation also increases. Transmitted refers to infrared radiation that is transmitted through an object or material. Due to most materials being opaque to the infrared spectrum, transmission does not need to be considered in most circumstances. In summary, reflected infrared radiation is the infrared radiation that bounces off of surfaces and carries information about the surface properties. Emitted infrared radiation is the natural infrared radiation that objects or substances emit based on their temperature and emissivity. Transmitted infrared radiation is the radiation from a source passing through an object or material. All types of infrared radiation are important in various applications, including remote sensing, thermal imaging, environmental monitoring, and industrial processes. Some materials are reflective in the infrared spectrum while others are not. As seen in this image, a hot cup of water emits a high level of infrared radiation that is visible to the thermal camera. The surroundings, which are at a cool temperature, including the tabletop and aluminum tray, emit a low level of infrared radiation. Due to its high reflectivity in the infrared spectrum, the aluminum tray reflects infrared radiation emitted from the hot cup of water. This produces a reflected image of the cup, which is also visible to the thermal camera. Notice that the temperature measurement of both the actual cup and its reflected image are nearly the same. The potential for reflected thermal radiation within the camera's field of view should always be considered in any application. In some applications, reducing a material's reflectivity with non-reflective coatings such as black paint may be necessary. Thermal emissivity is a measure of how efficiently a surface emits thermal radiation. It is a property of a material that quantifies the ability of the material to emit thermal radiation compared to an idealized black body at the same temperature. Emissivity values range from 0 to 1, with 0 indicating a perfect reflector where the material does not emit any thermal radiation, and 1 indicating a perfect black body where a material emits thermal radiation as efficiently as possible at a given temperature. Materials with high emissivity, close to 1, are good emitters of thermal radiation. In contrast, materials with low emissivity, close to 0, emit less thermal radiation and may generally be better reflectors. In the image above, a cylinder is shown at a higher than ambient temperature, at ambient temperature, and cooler than ambient temperature. Notice how the thermal image changes the object's color in relation to the background ambient temperature as an indication of the object's temperature. Now that we've discussed infrared and how it's utilized in thermal imaging, let's discuss two thermal cameras available from Protect-A-Wire. The PWTC-100F offers the following features: dual thermal/visible network cameras with integrated web interface, fusion of thermal visible images with 18 thermal color palettes, full scene temperature monitoring with up to 12 user-defined local regions, intelligent high-low temperature tracking, alarm condition detection, relay control, and network broadcasting features, a thermal resolution of 256 by 192, and with super resolution processing, which provides 1024 by 768 pixel comparable quality. The camera also supports many network protocols including ICMP, TCP, UDP, RTP, RTSP, DHCP, PPoE, UPnP, DDNS, and ONVIF. The PWTC-20F offers the following features: dual thermal visible network cameras with integrated web interface, offers a fusion of thermal visible images with 18 thermal color palettes, full scene temperature monitoring with up to 12 user-defined local regions, intelligent high-low temperature tracking, alarm condition detection, relay control, and network broadcasting features, a thermal resolution of 160 by 120 pixels, super resolution processing which provides 640 by 480 comparable quality. It also supports many network protocols including ICMP, TCP, UDP, RTP, RTSP, DHCP, PPpoE, UPnP, DDNS, and ONVIF. The Protect-A-Wire PWTC thermal cameras offer a complete smart thermal imaging solution which includes 24/7 scanning, fast on-camera analytics, IP connectivity with each individual camera, the lowest possible bandwidth required, and web-based configuration. With additional viewer software, the following can be achieved: tier level management, threat location management, a live view of both thermal and visual images, along with trending of historical data. Protect-A-Wire PWTC thermal cameras offer the following advantages. On-edge analytics make each camera an intelligent monitor for dangerous pre-fire conditions. Each camera provides multi-region detection for precise threat location. Smart analytics reduces false alarms under environmentally difficult conditions. Risk detection can be communicated real-time by multiple protocols. Dual thermal and visible cameras provide the best situational awareness. Network cameras build a complete solution with centralized data collection and control. The Protect-A-Wire PWTC cameras offer the following performance benefits: false alarm mitigation through dual sensor verification, and multiple threshold types providing application-specific configurations. Early warning. Cameras allow real-time monitoring and detection of pre-fire thermal conditions. Pre-fire detection technology greatly improves response time. Real-time awareness. Definable regions of interest within the camera view. and each region of interest can be set with unique monitoring and threshold parameters. Detection range. Detector sensitivity and range are related to the fire size. Standard fire is defined as a 1-foot square fire. The PWTC-100 detects a fire of this size at 65 feet or 20 meters, where the PWTC-20 detects fires of this size at 39 feet or 12 meters. Environmental awareness. The camera's alarm thresholds can be deltas to their environment. Changes of environment are considered in real time. The PWTC thermal cameras offer the right platform for your applications. The PWTC-20 Mini Dual Vision camera is designed specifically for real-time temperature monitoring of assets in close quarters, such as inside equipment cabinets. The PWTC-100 is designed for 24/7 thermal monitoring of all your critical assets, identifying issues before they become costly failures, preventing downtime, and enhancing worker safety. Protect-A-Wire PWTC cameras offer support for many different user scenarios. With a simple integrated web interface, users can configure the camera, preview the camera's video streams, view logged events, and interact with alarm functions. With additional software, each camera can be integrated into a network, allowing easy configuration and control of multiple cameras. The software provides aggregated views of analytics across multiple devices, real-time monitoring and data collection, and the ability to view historical trends. Each camera also supports monitoring via various protocols or methods such as MQTT, Modbus, or Relay Interface. Custom integration is also supported via ONVIF and a full-featured RESTful API with TCP protocols. In closing, Protect-A-Wire PWTC thermal cameras offer an advanced solution for thermal process monitoring and pre-fire detection. With their unique feature set, ease of configuration, and extensive options for integration, the PWTC series of cameras offer an ideal solution for a wide array of applications.
Thank you, Brian, for explaining the technical portion of the pre-fire visual thermal detection cameras. Now that we all understand how the cameras operate, as well as the multiple integration options available, let's focus on a few applications where this technology can be applied. As you may have noticed, we keep referring to the thermal cameras as pre-fire devices. The reason for this is that these cameras offer the ability to look for overheat conditions prior to an equipment failure or pre-fire event. Pre-fire condition monitoring allows for equipment or process shutdown, minimizing downtime, as well as minimizing the chances for a catastrophic event. Understanding the benefits of this pre-fire detection, we're going to focus on several applications where real-time temperature information combined with visual confirmation provides real value. Many power generation applications would benefit from pre-fire visual thermal detection. From substations to transformers or solar panels to wind turbines, our entire power generation grid has plenty of connection points. Appropriately placed pre-fire thermal cameras provide utilities and/or private owners a peace of mind. For renewable energy, the pre-fire thermal cameras can be used to find the hotspot in a solar field, or they're often focused on critical components inside a wind turbine nacelle. And speaking of wind turbines, let's move on to the next slide. Given all of you have signed on to the webinar today, we're going to provide a sneak preview into a revolutionary concept for monitoring the surface temperatures of equipment inside a wind turbine nacelle. Our partner, Planck Vision Systems, has created a battery-operated camera that runs on a track, allowing you to have mobility in your pre-fire visual thermal detection. The traveling camera will follow the track to complete its inspection of a predetermined area before returning to its base to recharge the battery. This device is designed to measure surface temperatures in hard-to-access locations or locations that require constant temperature surveillance. The use of a single camera on a track could potentially be more efficient than multiple cameras mounted in different locations, all viewing the same asset. Additional applications for this technology would include cable trays, utility tunnels, or other industrial processes, for example. Transformers are a great application for both standard fire detection as well as pre-fire visual thermal detection. Whether it's a small pad-mounted transformer or a large high-voltage transmission line, failures are a concern. Whether it's the insulation, bushing, or a coil failure, just to name a few, there are plenty of challenges when monitoring this critical infrastructure. For your larger transformers, the PWTC 100 series camera can be placed outside to monitor the surface temperatures. Conversely, the PWTC 20F camera can be mounted inside certain enclosures to provide additional peace of mind and pre-fire condition monitoring, as highlighted in the images on this slide. The use of the PWTC 100 series thermal camera to monitor hazard areas inside a transfer station to detect pre-fire thermal events is a critical aspect of a facility's safety plan. The thermal camera provides the ability to take early action to control a potential catastrophic fire in waste piles on the tipping floors or surge pits. The threat of lithium-ion batteries being embedded into paper bundles continues to be a concern. This threat can happen during normal business operation, or it can happen after the facility has closed for the evening. Having the ability to monitor surface temperatures and warn crews remotely of a pending thermal event can ensure the correct response is sent to these types of facilities. Charging stations are becoming increasingly popular around the world. Whether it's a charging station for an EV, an electric vehicle, or a charging bank for mobility devices like scooters or bikes, these infrastructure components share many of the same pre-fire detection challenges. As charging stations become more prevalent in our markets, keep up to date on your local codes and standards, as this is certainly a dynamic market that should see some sharp code increases and revisions within the next few years. In the first half of this presentation, Brian discussed the ability to define up to 12 zones within the field of view. The image below is from a paper manufacturing line where the roller is partitioned into 12 different vertical zones, and the pre-fire visual thermal camera is reporting real-time surface temperatures. This allows the operator of the facility to monitor their production line in real time and is a great example of how the zones can be configured. In this example, the zones are all equally sized, but with the custom configuration options, you can set your zone parameters and sizes to meet your facility needs. This is the second to last slide of the presentation, and it once again highlights the benefits of dual image capabilities. Having the infrared picture adjacent to the real video image really highlights the benefits of the two technologies being paired together in a single device. Clearly, in the upper image, the far right manifold has a significantly different surface temperature than the other two. The bottom images are where a three-phase power line connects to a facility. While the temperature appears uniform across the connection, this is another example of how this technology can be used to monitor for pre-fire conditions at critical junctions. The last slide I'll present today highlights the security features included in the pre-fire visual thermal cameras. As we've discussed, with the ability to define 12 zones in each camera's field of view, you also have the ability to configure the parameters within any particular zone. This obviously includes your temperature parameters, but you can also define motion and security parameters. If you know that a facility area or hallway should be motion-free during certain hours, you can configure the thermal cameras to detect motion and provide an outgoing alert as needed.
That concludes our presentation on thermal vision cameras. On behalf of myself and the ProtectWire team, I'd like to thank you for taking the time to attend our presentation today.
This concludes our presentation on thermal vision cameras for today. On behalf of myself, Brian, and the balance of the ProtectWire team, I'd like to thank you for your time in attending our presentation. As I discussed at the start of the webinar today, if you are interested in additional webinars or other ProtectWire featured products, we have a list of pre-recorded webinars that are available on our website. Thanks again, and have a great day.